Well, I'm totally delighted to be here and very honored to be selected as the keynote speaker. You can decide if it's appropriate. Please don't. You can keep the opinions privately. The title is the common application in the deferred. What's that?
Do you want to make it full screen?
Oh yeah, absolutely. Okay. Oh, this one? This one?
Yeah.
Okay. The title is the common application in the deferred acceptance algorithm in school assignment. And it's completely unnecessary for me to give the motivation, the general motivation, but I'll give a little bit more specific discussion about the common application, and that will enable me to give some sense of the general project. And I want to start by actually making 3 apologies. The first is that this was originally an empirical paper, and there will be empirical results, but we've struggled with some of the definitions of the data, which I'll comment on later. I think we sorted that out, but only very recently, so the apology is there isn't a working paper version. But we hope to have that very soon. And the second, I think, is actually much more important, which is that this is my first foray into school assignment and school choice, having done so much work on higher education as a focus. And so it's with a lot of trepidation that I listen to everyone's introductions and come to present something on school choice, because although I followed this literature and feel like for many years and have been excited about it for all this time, I am a novice by comparison to everyone else in the room. So I look forward to learning more about your work, and especially how it bears on what we're doing in this paper. There may be that Parag certainly knows this work really well, but it may be that we have some blind spots, especially since I'm relatively new to the literature. It'll be helpful if you can point that out. And the third point is that this is primarily going to be oriented to American educational assignments. So if you know, if you've been working in other areas, as many of you have, I look forward to learning from you how these results do or don't apply outside the American context. The common Parag actually approached me to work on this paper, and it was because I think the common application is a very standard element in higher education, college admissions in the United States, but it's relatively novel in school choice K-12 in the US. And in the college, we'll talk a little bit more tomorrow at the lunch roundtable about college access around the world in Europe and the US. We've been asked to make short presentations in advance of the roundtable discussion. But the critical point is that access is a big problem in the United States and elsewhere. And one of the reasons is that students from low-income backgrounds find the American college admission system complicated, tend not to apply to the best colleges, tend not to be represented, even at the level of their achievement. So the common application has been around for quite a while, but it only gained popularity in the last 20 years or so, and it's become almost a standard part of the application process now. It's a single application which you can use to apply to most of the prominent colleges in the United States. Some of them will require additional materials, but the common application to colleges is a series of ordinary fields. You know, what are your activities? What are your accomplishments? What are your test scores? You write one essay, you get some recommendation letters. Some colleges may ask you to do some supplemental material. But the idea was, so many of these colleges were requiring very similar things, but asking them to be unique. So you had to write one essay for one college and another essay for another college in different forms. So all the forms are equivalent. And the standard view on this, as represented by the Harvard admissions director, William Fitzsimmons, he says we're leveling the playing fields. So the colleges see this as an element of access. That the common application is reducing the cost of completing the application to once you've done one, is reduce cost to additional ones. And the view is that students who are from relatively poor families don't have as much expertise, don't have as much help from school counselors. If we can reduce the cost to them, that's got to be a good thing. So that's the perspective from the college view. And there's been a few studies almost all of them based on empirical studies, almost all using the same methods, which is we look at applications before and after, and what happens in any period of time. A few more colleges adopt the common application. There's been more and more that have adopted it. Let's see what happens to the colleges when they adopt the common application, and occasionally let's see what happens to the competitor when your competitor has adopted the common application. Most of the results in these papers suggest that adopting the common application draws more applicants to your college. There are some suggestions, although it's much harder to find any instrument to identify the effect on individual students, but there's also some suggestions in the paper by Jonathan Smith and also by, I think it's Daniel Classic, that individual students may apply more as well. There's some nuances to this literature that I'm happy to talk about if you're interested in them. But an interesting point is that the common application has not been a theme, to my knowledge, in K-12 or school assignment below the college level. And I think for two reasons. One is that it just hasn't been prominent, and nobody's done it. We're going to look at a situation in Chicago, the same kind of before and after idea, to see what happened when the Chicago public schools adopted the common application. So that's reason number one. It hasn't been prominent, but that's the motivation for this paper. We now have an opportunity to see if the same kinds of results hold at the elementary school, kindergarten level, in fact, as at college. A second point is that all of you, I think, have been involved in studying, or many of you have been involved in studying much more sophisticated assignment mechanism design mechanisms. And by comparison, the common application has actually got a lot of flaws. So it wouldn't be a natural thing to think about if you were thinking about top trading cycles and a variety of other assignment rules. But that also means that when Parag came to talk to me, we didn't know of any work that anybody had done at the K-12 level on the common application. Originally, this was mostly an empirical paper, but partly because we got caught up in some issues with the data that I'll talk about, more because we got excited about the deep connections between the common application and the deferred acceptance algorithm. It's morphed from into much more of a theoretical paper. So I'm going to do three things, and the first two of them are theoretical. One is I'm just going to talk about the connections as we see them between the common application and the deferred acceptance algorithm. The second is I'll look at some results in a decentralized Nash equilibrium of the game. And then lastly, I'll present some empirical results, which are, as I will tell you, the most preliminary part of the paper. So we're going to compare the deferred acceptance algorithm under two different versions of the common application. What's going to be particularly important is the random priority rule that I know some of you have studied. And the key difference between common application, at least as practiced in Chicago and elsewhere, possibly elsewhere at the K-12 level, is the schools are not allowed to submit preferences over students. And so this brings into play all of the recent work on tie breaking and other elements of K-12 that are really not at all present in college admissions, because college admissions, there's explicitly always the colleges are making choices based on detailed evaluations of students. And in the language of the mechanisms, the colleges are going to have preferences, and there may be priorities within. The colleges may be giving priorities to some students, often in subtle ways over others. So it's a much more complicated mechanism. But the one point I'll make is the common application could be particularly valuable at the college level because the colleges can submit their preferences. It may be that the colleges actually are better than students at identifying, in some instances, which students are going to do well uniquely well at our institutions. So if the colleges are particularly good at reading the applications and saying, you know, Andy needs to go to one kind of college and Antonio needs to go to another, the common application is going to be very useful at figuring out that kind of matches, because the colleges can read the applications and put that information into the decisions. None of that's happening at the K-12 level. So I'm going to report fairly negative results about the common application at the K-12 level. But you shouldn't think of that as a condemnation of common application overall. I think it could well be much better suited to college settings. It goes without saying that there's been a big literature on algorithms. I'll talk about the related literature in two different stages. For right now, I want to talk about the related literature to the specific connection between common application and deferred acceptance algorithms. There's been many notable papers, in fact, a number written by folks in the room. And as I said, I'm very humbled and a little bit insecure about talking about this topic, but I'm going to go ahead. And then the second part is that the very particular algorithm that's most connected to the common application, as we find, is the probabilistic serial dictatorship, or random priority mechanisms. And there's a shorter literature on this topic. In particular, I believe Bolgnaya and Moulin introduced the idea in 2001, observing that there are some flaws to the random priority mechanism, which has been practiced in many instances. And then there's more recent literature, most recently with Che and Kojima in Econometrica, in which they observe that, in fact, in large economies, the two systems are relatively similar. So we're going to be talking mostly about the random priority, but everything we do will relate back to this full literature comparing those two related mechanisms. To make it a common application into a deferred acceptance algorithm, you're going to have some preferences from the schools. And I explicitly said that in Chicago, the schools aren't allowed to have preferences. So the only way to convert to the deferred acceptance algorithm is going to be to create some fictitious preferences for the schools and then run them through the algorithm. Already that's starting to sound like a kind of a weird idea, and I think that's, again, part of the reason the common application may have been little studied at the K-12 level, that it's kind of in some ways there's an inherent contradiction, and when you start to behave as though the schools have no preferences and then generate the preferences for them, it just feels odd. But there'll be two different versions of this. One is going to be, we imagine that the schools we generate a single strict rank order over the students, and we use it for every school. So the correlated resolution of the uncertainty about the school preferences, or we do some sort of IID choice over rankings of students and have each school submit a different ranking. So those are going to be the two different systems. Each one of them is going to have a particular connection to the standard versions of deferred acceptance and other applications of it, but quite different. So as a motivating example, and I'll tell you that we're going to end up with one of them looking just like random priority, dictatorship, and the other one looking like common application. It's always helpful for me to get into an example, and so we have one here. And this is going to be a two-school example where one school is more popular than the other. In this case, it's going to be that 3/4 of the people prefer school A to school B. We do everything in measures so that there's a unit measure of students from 0, could be from 0 to 1. But in this case, that's just discrete types. Everybody who, and there's not going to be any, the strength of preferences aren't going to matter in what we're doing here because everything is just going to follow ordinal rankings. But we are going to have the schools each admitting 1/3 of the students. So when everything resolves, 1/3 of the students will enroll in school A, 1/3 of the students will enroll in school B, and 1/3 will not be enrolled at all. And 3/4 of them, if given the choice, would prefer A. So with identical school rankings, imagine that so each school is going to have the same ranking of students, and there'll be a lot of students maybe. Doesn't really matter how many, but it'll proceed along the following lines. If you ran the deferred acceptance algorithm and you knew that each school had submitted the same rankings, well, the first round, we'll get the same results with schools offering and students offering, so I'll talk about the schools offering. In the first round, each school will offer to 1/3 of the people. Now, if they have identical rankings, each school is going to offer to the same 1/3 of the students. So 1/3 of the students will have offers from both schools, 2/3 of the students will have offers from nobody. So that's going to mean that the students choose, that first third of the students will choose, and they'll choose their preferred schools. 3/4 of them will choose school A. 1/3 times 3/4 is 1/4. So 9 out of the 36 will choose A, and the remainder, 3 out of 36, will choose B. I use 36 as the divisor here because that'll be relevant when we do the other version where the schools have independent preferences. And what you can see here is that already a lot of choice is being involved on among the student in the division of students. A lot of matching is already going on because everybody who was offered had the choice of both schools. So coming back to my earlier work on revealed preference of various sorts, this has the nice feature of getting a lot of revealed preference into an ordinary matching out, into what seems like an ordinary rule. In the end, if you keep running this algorithm, school A will fill when 4/9 of the students have been offered, because 4/9 times 3/4 is 1/3. So that means the first 4/9 of the students have offers from both schools, and then school B has to continue offering, and then between the next 2/9 of the students will only have offers from B, and they have to choose. That's what they choose. Okay. Now, if we did the other thing, we had the schools make independent offers, and if it's a large enough population, everything will even out. Both schools will start being offered by 1/3. Both the schools will each offer to 1/3 of the students, but 1/3 times 1/3 is 1/9. It has to be a double accident that you get offers from both schools. So instead of everybody who had an offer choosing between having two offers, only a fraction have offers from both. So 1/9 will have offers from both schools at that point. 2/9 will be offered just by school A. 2/9 will be offered just by school B in the first round of the algorithm. So what's going to happen is that 1/9 of them will get to choose their favorite one, and the other ones, it's just an accident which one made the offer to you. Some of these people, two people who've been offered by just one school will get offers from the other one in later rounds of the algorithm. But the thing to observe right away is that at the beginning, both schools are actually going to be much closer to being filled after round 1 than they were in the identical preference case. And the reason is that it used to be that just 1/3 of the students had any offers at all. Now 5/9 of the students have offers. So in a way, we're actually pretty close to finishing the offers already, because there can't be that many more students who are going to get an offer from either school, given the 1/3 capacity for either one. In fact, it's a quadratic equation. The eventual solution is about a little bit under 40% get admitted to A, a little bit under 50% get admitted to B. These are lower values. It used to be 4/9 and 2/3. These are lower values than in the identical preference case. And in fact, as opposed to 4/9 having the choice of both schools, here it's only 17.5% have the choice of both schools. So there's a lot less revealed preference involved in this independent ranking case. And you can see this very clearly, the consequence immediately. If 2/9 of the students have offers just from A and 2/9 of the students have offers just from B, but we did it randomly, we have no reason to believe that those 2/9 of the people who were offered by A really wanted to go to A. And in particular, we don't have no reason to believe that the 2/9 of the people who were offered by B really wanted to go to B. There were two types of students, some like A, some like B. We've kind of mixed them up here. And so clearly there's going to be a room for some trade. This is not going to be pairwise stable. The other mechanism is going to, with identical rankings submitted by the schools, will definitely be pairwise stable, because 4/9 of the students had the choice of both schools. Anybody who ends up at school A also had an offer from B. And so that's really the best you could do. I see that nobody's been asking me any questions, so please, this would be a great time to start. Yes?
It has to be pairwise stable. I mean, you are using Get and Shapley?
No. So it has to be pairwise stable. OK, great point. It has to be pairwise stable according to the preferences that have been stated. But remember that the school preferences were just generated at random. They don't represent anything. The school preferences were generated at random so we could run the algorithm.
So it's a stability among the students only.
It's a stability only among the students. So, this is a really great point. And it comes back to my earlier statement. I stated it a little bit awkwardly as well, because it's hard to explain. But it comes back to the earlier statement that it's strange to run in some sense, to run a DA algorithm when you immediately say the schools don't have preferences, because you have to generate preferences to make it work. That was your question. Okay.
So if schools are indifferent at the outset to students, what's the rationale for using the school proposing version?
Oh, so in this instance, the student well, all our theorems are going to say that the school proposing and student proposing versions are going to overlap. So you're right. If we could imagine using the student proposing version, if this example is simple enough, I think that the results come either way. So the rationale for using the school proposing version was easier to explain. But I believe we can talk about this later. I believe that the two rules are going to overlap, particularly with large populations, and I'll have some results. I'll make some comments on in particular cases where we specifically explain that the school and the student proposing versions are the same. Yes, Antonio.
There's some relation, let's not say, with this paper by and Yasuda, but not the AAR paper, the one accepted in AAG recently, in which they talk about single tiebreakers versus multiple tiebreakers.
Yes.
And they conclude that without pre-existing priorities, the multiple tiebreakers result in ex post inefficiencies, whereas
yes.
single tiebreakers are okay.
We have to think about this a little bit more, and I would love to talk with you about this. I think that there may be some very specific connection to that result. We've thought about that. It's obvious that there's some relationship because this is a case of the tiebreakers are very, very important. But let me talk to you about that separately, because that clearly could be a deeper relationship than what we realize. Okay, so now, with this example in mind, our point is that, in fact, the identical ranking system is going to prove to be very similar, in fact, identical to the random priority serial dictatorship. So we'll have a theorem about that, but you can almost see how that plays out, that the people who were lucky enough to be offered early are going to have the choice of both schools. That's like being the first in line in a serial dictatorship random priority situation. With independent rankings, it's going to turn out to be a lot like a common application situation in which each school, I'm going to have to be careful, I'm accustomed to saying college, each school has an admissions probability, and the admissions decisions for one school are independent of the other, with everything being at random. So here school A would be admitting 37.7%, school B 43%, and those admission decisions would be randomly chosen. And the claim is that if in a common application, if the schools use those probabilities, you get the same it has to be in probability now, you'll get the same probabilistic result as you would get in the deferred acceptance algorithm with the school submitting independent rankings. So just to formalize this slightly, we are going to be assuming that this isn't going to be an equilibrium model. We're going to be assuming that the students are just submitting preferences over all the schools, and that there's some matching algorithm that's being used. The capacities of the schools are fixed, and that typically we assume that the sum is less than 1. All we have to assume is that the students have strict preference rankings. That makes things a little bit easier. We'll assume IID draws from a known distribution over possible rank orders. And to make things even simpler, we'll assume that the students prefer assignment to any one of these S schools to no assignment at all. I think if that wasn't the case, we could have an S+1 school that would be no assignment. But we stick to just the S. And so the first result, and it's almost immediate, is that there's an exact equivalence between the deferred acceptance algorithm with identical ranked orders submitted by the colleges generated at random to the random priority serial dictatorship. And the reason is that if all the schools are submitting to the same order, it's a rank order. And that's like putting people in line in the serial dictatorship. And so if you go person by person by person, it has to be the same assignment. And the proof falls immediately by contradiction, because you say, well, if it isn't the same assignment, there's somebody who's the very first person in the order or in the line who's making a different decision, different assignment under the two mechanisms, and then, well, that can't be. If the person would make a particular choice under serial dictatorship, well, all those whatever option that person would choose would be available in the deferred acceptance algorithm, and that's where the person would get assigned. So this, I guess, in some sense, once you see the relationship is immediate, but it was mildly surprising to us, because when we first asked the question of ourselves, what is going to be the connection between the deferred acceptance algorithm and anything we're doing here, we didn't know. Now we think we do. So the common to make the comparison to the common application, I have to define the application equilibrium. And as I said, that's a series of admission probabilities such as expected enrollment after the students make their choices among any schools that make offers to them. Expected enrollments have to be the capacities of the schools, given independent admission decisions. Making and
Did you define what the common application was? Because I'm
Oh, no, I
understanding from
didn't.
the example
I
that
didn't.
It's like independent decisions.
yeah, so that basically I'm trying to define it here.
Okay.
So the common application is going to be each school has a probability. It makes offers to every student independent IID. So in the example, just like in the example, school A, it was the end 37.6% was their probability. So it goes person by person by person. It flips a coin, and some people get offers and some people don't. If you're in the 37%, flip a coin, get a random number between 1 and 1,000. If it's between 1 and 376, you get an offer. Then we flip it again for the next person, and so on. So everything's independent. So that is and it's assumed implicitly that in the common application here, all students who have submitted a priority order, that's like applying to every school.
But why is it natural to think that in a system with common applications you would have independent decisions? I mean,
it's a common application system for the school choice situation in which the schools are not allowed to have priorities. So this is yes, everything. I should be clearer that I'm defining everything is supposed to be for the context of today's results only. And when I made the comment that the common application could be better for, I believe it's ultimately be better for colleges than for K-12, it's precisely because this definition isn't going to be the right one for colleges. Yes?
Isn't there a capacity for a school then?
There is a capacity, KJ, so that's going to be determinative of the probabilities. The probabilities have to be such that each school hits its capacity. And that, to make things easy, an expectation. And so we want to think about large populations for this reason. And I'm making things a little bit easier for myself by assuming that the expected enrollments are less than 1. So I don't have to worry. There might be some issues if the expected enrollments add to 1.
So just to be clear, so there's a positive probability that you accept by every student.
A positive probability, yes. If college A is accepting each student with probability 37.6%, it remains possible that they accept everybody. So in fact, that's a key point, that the algorithm is designed, if you generate the preferences for the schools independently and run it through the algorithm, with probability 1, they hit their capacities. If you run the common application as I've described it, it's very possible that the whole thing messes up. Some schools oversubscribe, others undersubscribe. So as Estelle suggests, all results are going to have to be, equivalence results will have to be in probability. And the natural way to think about this is in large populations. So the law of large numbers is going to tell us that if this messes up, it doesn't really mess up by very much. We're actually arbitrarily close to the capacities.
So
yes?
School's payoff is just to be as close as possible to the capacity and negative.
Yes, that's right. So if you were to model this as a game, you would say that what the schools are just trying to get to their capacity.
They're not maximizing anything?
They're not allowed to.
So the probabilities are designed only to reach the capacity.
Only to reach the capacity, and that is true in our empirical context. That is, well, our empirical context proves to be complicated in a variety of dimensions. From what we can tell, the rules are designed. The rules are designed so that the schools are only supposed to do that, and from what we can tell, that's all that they're doing. Oh. Wait. And in fact, there's an interesting, the proposition is that there's a unique common application equilibrium. It's actually, I'll spend just a moment mentioning the motivation of the proof, because I think it's interesting and it plays a role in a variety of other things we do in this paper. Suppose that there were two different sets of probabilities that actually hit the capacities for every school. Well, in one of them, some of the schools would have to have a higher probability of admission than in the other. And some of the schools would have to have a lower probability of admission than the other. Suppose that we have a P vector and a Q vector, and then you could isolate the schools that have the higher probability in the Q vector, call that set schools set 1, and compare them to the schools that have a lower probability of admission in the Q vector. You switch from the P to the Q. Let's call that set 2. And what would happen is that set 1 of schools under the second, when they increase their probabilities, they may be competing with each other in some kind of complicated way, but on the aggregate, they're going to actually increase their enrollment. And in the aggregate, the schools that reduce their probabilities are going to reduce their enrollment. So there's no way that both of these could clear the market and hit these K capacities. So this uniqueness is actually going to be very helpful for us in a variety of proofs. But it's at least useful for this setting. It's useful to know that we're just comparing to exactly one thing. There's no ambiguity about that. And here's the probability statement that if the schools submit independent random rankings, then the DA algorithm is going to match students to schools with the same probabilities as the common application. This really only has meaning in the large population, I would say. And the natural way to think about this in that setting is imagine a large but finite population of students, generate the independent rankings, run the school proposing algorithm, which in fact is going to be the same as the student proposing algorithm. Run the school proposing algorithm. Well, the schools are going to go down their list a certain level to make offers. But eventually, in each round, you go down the list. If you're not full, you go down your list a little bit further and make additional offers. Eventually, with a finite population, the algorithm has to converge and with the right assignments to every school. So in the end, every school has gone down its list to some degree, and it's filled its capacity. Well, you can then just interpret the proportion of the distance down the list each school has gone as its admission probability. And that's going to have to be the same as what would happen in the actual common. And then essentially by just taking the probability, by just thinking about equation by equation, each school's admissions rules and what each school's enrollment total. To enroll at my school, well, if I'm school 5 and you have order 1, 2, 3, 4, 5, 6, 7, 8, all the way down to 100, there's 100 schools. If you're going to enroll at school 5, it has to be, with that order, it has to be that you weren't admitted to any of the first 4 and you were admitted to school 5. That's one of many ways you could choose school 5. Put them all together, and we basically have the same market clearing conditions under common application as you would have in the convergence condition for the deferred admissions algorithm. Deferred acceptance algorithm, yes.
Do you know this paper by Azevedo and Leshno?
And-
The paper Azevedo and Leshno where they propose similar environment as yours.
Okay.
Schools, schools are random drawing their preferences, and in case this random draw is full support, they get uniqueness of the core, which means that school proposing and student proposing are going to be the same.
Okay.
And
So
they also have like similar type of admission threshold that would clear the markets.
Right.
So it looks similar to common application, and they show that this way of approaching the problem is equivalent to dealing with just deferred acceptance.
Okay, so I didn't know this. I don't know this paper, and it sounds like we've just replicated their result.
Sounds similar, yes. Similar.
Which is great to know.
Replication of theoretical results is useful.
Better than if you don't get this. You try and you get a different result.
Yeah.
And part of the reason I was excited to come and present today is to learn about the literature we don't know. As I said, Parag is very, very steeped in this literature, but when you have 3 co-authors and one is a doctoral student, another's a novice in the literature, and one expert, you can have gaps. So I'm delighted. I'll get the reference from you afterwards if that's okay. And so I guess the obvious point then, the background, going back to the example, I'll start with the second result, then move back to the first. The random priority result mechanism is going to produce pairwise stable outcomes with respect to student preferences alone. The common application does not, even though it's running through a deferred acceptance algorithm, because you're getting distortions due to the fact that you're treating the preferences that are reported as real preferences when they're not. This translates with 2 schools into a stronger result of stochastic dominance, which is that the random priority algorithm is going to stochastically dominate the common application algorithm. So the one version, the identical preference version, is going to stochastically dominate the independent preference version of deferred acceptance if there's 2 schools. And the reason is the real preference argument and the stable matching argument. You're going to get everybody who chooses the more preferred school will have had the choice of the other. So that's going to get essentially as many people to have their first choices as possible in random priority or the equivalent identical preference version of deferred acceptance algorithm. So that seems like a really, but you don't get that in the common application, specifically because you get mismatches where one person prefers A but is assigned to B, another person prefers B but is assigned to A. The pairwise stability works directly back into the stochastic dominance result with 2 schools. That seems like a strong result. It seems like it ought to generalize beyond 2 schools. It does not. And for that particular reason that we can come up with examples. I have one that I can show anyone if they're interested, and will ultimately be part of the appendix to the working paper. You can create examples where making the best first choice assignment involves a displacement of so getting the maximum people assigned to first choices may mean some distortion of second choices. So, and in fact, you can create examples where not getting as many people assigned to first choices means getting more people assigned to second choices. And so that was disappointing to me when we realized that, but the stochastic dominance result does not generalize beyond 2, but the pairwise stability does.
So one way to reinterpret your result is to say that it's a comparative statics result between when you move from independent priorities to purely, completely, fully correlated priorities. So these are two extreme points. Could you have a result that says the more correlated the school priorities are, you still get a stochastic dominance result saying like there you have 2, and then you need to figure out the proper order, of course. But you have 2 systems of school preferences. One is more correlated than the other. Do you get?
That has that's a great idea. That has the feel of something that ought to be true.
Yes.
And I hadn't thought about it, but
Because that's interesting.
it's incredibly interesting.
Sometimes you are comparing 2. Your framing currently is about 2 different mechanisms, but in practice you could have different school systems with
Absolutely.
priorities dictated by policy, and saying like, how should policymakers think about
Absolutely.
the impact of priorities on the outcome?
Oh, and one important point, as soon as you get this result that the stochastic dominance does not go beyond 2, that also tells us that we can't do much with cardinal utility, that our results aren't going to work well in cardinal utility situations, because everything was done with ordinal utility, and going beyond 2 but if we put in cardinal utility, if we can come up with examples where stochastic dominance goes the wrong way, we can also then assign cardinal utilities in those cases in which the expected utility of students is going to be higher under the common application than in the random priority, despite the fact that it seems like the wrong rule. So with this as the background, and I realize that I see Antonio looking worriedly at the clock. We're going to be fine. I want to talk a little bit about the Nash. So that's really just a sort of an interesting, that's all a backdrop to how to think about what happens when you actually implement this in practice. And when you implement it in practice, it's going to have to go beyond the ordinal rankings into a Nash equilibrium setting, where we want to compare the decentralized application system that was used by Chicago Public Schools in the past to the common application system that they use today, and use the comparisons in theory to generate hypotheses and present some results on the hypotheses. I have to make things a lot easier on myself to get anything to work, so this is going to be a much more restricted model, but with the caveat that now we can think about this as a baseline, and that beyond the case we're going to assume, do I even say this? We're going to assume symmetric distributions of preferences. I think I might not have even put it on. Nope, in fact, so yes, I apologize. Oh yeah, I guess it's right here. The schools are identical ex ante. So that the students are going to have utility values over S schools, but we're going to assume a symmetry that was not assumed in the earlier example or in the earlier framework, so that each school is equally likely to be preferred, or that if this is going to give these utility values will give rise to a distribution over rank orders. Effectively, that says all rank orders are equally possible, and furthermore, the utility values are going to have to be jointly distributed in some symmetric fashion. We're still going to have, and we're going to have, to make things simpler as well, I'm going to assume the same capacity for every school. That's not actually necessarily as important, but it'll simplify the presentation and a lot of the exposition. we can come back to, if you have any worries about this, we can come back to the fact that this is now an extremely stylized model. And so the predictions could be problematic with regard to the actual situation, where we'll see that the schools in Chicago are nowhere close to being symmetric in any fashion. Under the decentralized rule, we're going to assume a cost C per application. Under the common rule, we're going to assume a cost C, but you get to apply to all schools with that cost. And the idea is you fill out the paperwork, and once you've done it once, you use the same piece of paper for every school, or you even go to a website and you say, I filled out the paper, now here's all the schools I want to apply to. I think that's actually, in fact, how it works in Chicago, that you complete some background information, and then whether it's on a website or a piece of paper, you just check the boxes for all the schools you want to apply to. There's actually hundreds of schools that are listed, and a maximum of 20. So I don't know the logistics of how they manage the listing of 20 for the kindergartens, or if they actually list the names of every single school in a very unwieldy fashion. But we're assuming here, for the theory purposes, that once you've applied to one, you've applied to all of them. So that's a slight deviation from the actual, where you apply to a maximum of 20. There's a separate relevant literature related to this equilibrium model. And again, this is almost all at the college level, where Sade, Lewis, and Smith, in a really lovely paper, demonstrate the complicated maximization problem faced by students, even in a two-college world, where you're trying to decide your optimal portfolio of which schools to apply to. They intentionally choose an easy setting in which one school is preferred by all students to the other. But then a lot of students are thinking, if there's preferences for the popular school aren't that strong, they're thinking, you know what I should do? I should apply only to the second school because I don't have such strong preferences as the first one, and it's really popular, and it's pretty costly to apply. So they explore that situation. And you can think of the common application. They don't talk about it very explicitly, as I recall in the paper, but you can think about the common application as one in which in an extreme case, the costs are reduced, or I don't believe they talk about the cost of the second application being reduced, but it clearly would simplify the decisions relative to what they describe in their model. At the same time, and I'll make a reference to my earlier work with John Levin, when we studied early applications, we identified the importance of that as a signal to colleges of your interest that actually helps to clear the markets by improving matches. Again, this is a two-sided that's a two-sided matching world, or one in which the students have distinct preferences that they can signal. And if you have a common application, you lose a certain amount of signaling. It doesn't have to even be an early application. If there's a rule that you can apply to just one school, or there's a cost per application, implicitly in equilibrium, you're going to get some signaling. So in Sade, Lewis, and Smith, it's depending on, it's either the students who think they have a better chance of being admitted, or in a world where the preferences vary continuously, it's the students who have the strongest preferences who are going to apply to the more popular school. There's a separate literature from the college admissions side. Yuan Chuan Lien, who is a student of Muriel Niederle, has an older paper that I think is still a working paper. Che and Co. have a more recent paper. And this is a mildly, these papers do slightly different things in addition to what I described. They really look at the challenge to colleges of trying to figure out who to admit in a world in which there's a cost to losing a student to another college. In Lien, it's that your ranking goes down because you look less selective. In Che and Co., it's more about trying to target a particular capacity and finding a big loss to miss targeting. If you under-enroll, you have to go to the waiting list. Maybe that's a cost. If you over-enroll, you have overcapacity, and that could be even bigger costs because you don't have the facilities in place to house all the students. And so in what these models are saying for the common application is that the more applications you have, the more you get congestion, and the colleges are going to have to do things to try to look for students who are going to choose them. And that may lead to, even in a single-dimensional ranking world, it may lead the colleges to go for students who actually are lower quality because they think it's less chance that that person's being admitted to the other school. And so that's what both of these papers are emphasizing is a non-threshold rule. I don't just admit the students who are the highest, I actually try to target. And Che and Co. talk about even further the possibility that colleges may want to distinguish themselves to create niches to avoid the problem of overlapping competition and the possibility of losing more and more students to other schools. So these are related themes, but not exactly the same as what we're doing here. And what we're going to do is particularly now look at many of these same issues, but again, mostly from an ordinal ranking perspective, again from the market design, a little bit more from the market design perspective, although we're in an equilibrium setting. So in this instance, since the colleges are symmetric, it's going to be even easier to observe that in any common application equilibrium, there's going to be a unique admission probability that all the schools use. And essentially, as the admission probability goes up, more students apply. And if you apply to every college under the common application. So as the admission probability goes up, the enrollment goes up in a symmetric fashion. We're just looking for a symmetric equilibrium. And so there just has to be one probability that clears all the markets. Essentially, if all the schools use too high a probability, too many students apply, and they overfill, all of them do. But if all the schools use too low a probability, it's the opposite. And that's the second point. Now, I make this point in a little bit more elaborate detail than might have been necessary because that very same argument does not apply in the decentralized case. So we're going to get a unique symmetric equilibrium in the common application rule, single cost for applying to all schools. We actually don't get a unique equilibrium in the decentralized case where you choose your applications one at a time. This is a point actually that was made, I think particularly highlighted by Sade, Lewis, and Smith, where they say that a lot of the natural market intuitions fail in the portfolio world in which you only want to attend one school. I'll run through it.
Is it in mixed strategies or something?
Well, let me show you the example. It doesn't have to be. So here's a second numerical example to make this point about the multiple equilibria. Suppose that I'm using the same, trying to use many of the same ideas as before. Suppose there's 8 n students in 2 schools. Each school wants to enroll 3 times n, where n is a big number. So each school wants to admit 3/8, and the total is going to be 3/4. Imagine that half of the students have utility values where they really like A better than B, and the other half like B better than A. So it's 8 and 4 and 4 and 8 to make things natural. Well, if each student applies to one school, then they're going to segregate. People who like A are going to apply to A. People who like B are going to apply to B. Half of the people applying, I want to admit 3/8. So each school would then admit a 3/4 probability. 1/2 times 3/4 is 3/8. And at that point, you'd say, well, do I want to apply to the second school? Well, I'm applying to the first school, and I'm getting 8 with probability 3/4. There's still probability 1/4 I didn't get admitted. And I might want to apply to the other school with probability 3/4. So that's something like 3/16. So if C is low enough, if C is low enough, I might actually want to apply again to the second school. And so let's do the actual calculation. My marginal gain from applying to the second school, ignoring the cost, is 3/4 times 1/4 times 3/4 is 3/16 times my utility value of 4. That's going to give me the 3/4 lower bound. So if C is less than 3/4, this would fail applying to one school. There would be too much utility for applying to the second. But if C is greater than 3/4, then this idea of P equal 3/4 one school application, that's an equilibrium. And if you're not following in real time, that's totally fine. You should just get the idea that if the cost is high enough, can't be too high, otherwise I don't apply to anybody. But if the cost is high enough, I won't apply to a second school, and I'll get an equilibrium. But the interesting point is that if everybody applies to 2 schools, what in fact happens is that the market now has to have a lower admissions probability. And this lower admissions probability is going to increase the value of your second application. That's the intuition from Sade, Lewis, and Smith, where they say, boy, this is a hard problem. Because you can't just identify you have to think about what everybody else is doing, how that applies to the probabilities, and you can get what they describe as reversal. So this is kind of a reversal. More people apply to more schools. That's sort of self-fulfilling. And in that instance, you're going to end up getting this range between 3/4 and 1, where applying to both schools is actually valuable. And this comes about because now the value of the second application is 1/2 probability you didn't get admitted to the first. times 1/2 probability you get admitted to the second, that's 1/4, times value 4 for the second one. 4 times 1/4 is 1. So this range from 3/4 to 1 is going to generate multiple equilibria. So when we generate theorems, we're going to have to generate theorems that apply to all of the decentralized equilibria, comparing them to the unique common equilibrium. And all the theorems are actually pretty natural. So I will present them in a fairly rapid fashion so we can get some time for the empirical results. But I'm happy to talk about any that interest, if they particularly interest you. So every school has to receive more applications and also has to then generate a lower admissions rate in a common applications equilibrium than in any symmetric decentralized equilibrium. And the reason is fairly obvious. It's a little bit like my argument that there was a unique common application equilibrium. Let's start with the lower admissions rate. If you don't receive a lower admissions rate in the common application equilibrium, then more people will apply. And so I said my admission rate is 50%. I get too many applications. If I admit 50%, I over-enroll. So that's not an equilibrium. And then I also have to receive more applications, because if I don't receive more applications in the common application equilibrium, I won't fill my class. I won't be admitting enough. So these two things go together. And what that also means then is that in this case, we now get a strong stochastic dominance result, but it's all coming about from it's all very specific to the assumption of symmetry. So that the ordinal rankings of the students are going to stochastically dominate in any decentralized equilibrium. The ordinal rankings of the school assignments for students will stochastically dominate the ordinal assignments of the unique common application equilibrium. And this is actually fairly prolonged proof, but I'll just describe the intuition. And the intuition comes about precisely from the ordering of the admission probabilities, that in the decentralized, and because of symmetry, we avoid the Chardet-Lewis-Smith strategic problems, where you sometimes say, it's too costly for me to apply to my first choice, I'll only apply to my second. Everything's symmetric, so all the colleges are equally popular. So the natural thing for any one person to do is to apply in order, first choice, then second choice, then third choice, and stop when the cost is too high for the next one. So immediately, since we have the ranking of the higher admission probability in the decentralized case, that means there's immediately a better chance of getting to your first choice college, first choice school. And that is going to propagate all the way through. And our proof shows that ranking propagates through not just to the first choice, but to the second choice and further ones to produce a stochastic dominance ranking. So that's our nice result that says the ordinal ranking system is going to produce a better outcome than the decentralized equilibrium is going to be, the old system is going to produce a better outcome than the common application system. Even this has to be tempered a little bit because I haven't looked at the application costs at all. So there's still an argument in favor of the common application that if it's really costly to fill out the paperwork, the common application is saying you still only have to fill out one. There's a sort of paternalistic view on this, I believe, that comes out of behavioral rules that many of you may be familiar with. That in fact, I think if you believe that school choice is important, as I think we all do, we believe that the assignment really matters. And to ignore the cost of application effectively requires the paternalistic step of saying, when people spend a lot of time, when people are deterred by these costs, they're making mistakes. Because these matches are really important, and these costs, however, nobody likes to fill out forms, but no matter how bad the form is, it's not that bad by comparison to the value of a better match. So if you're willing to take that paternalistic view, then you probably take this proposition more seriously than if you're actually truly worried about the costs that are incurred on people from the application system itself. Now, coming back to the original point, the folks in colleges say, well, the common application is evening the playing field. And this was, in fact, a clear motivation in Chicago, that they felt that they'd observed higher income families were submitting more, students from higher income families were submitting applications to more schools than were students from lower income families. That ought to be, so this is that we ought to be thinking that this is a way of evening things out and producing better representation, more diversity of student types, whatever type you're thinking about, across all the kindergartens. And but I'll just tell you in words, we have some theoretical results, but if imagine that we're talking about insiders and outsiders. If insiders are already applying to all schools, then introducing the common application has to be good for the outsiders, because more of them are going to apply to all, more of them will expand their applications, and they're just catching up to where the insiders already were. However, if that's not the case, if the insiders were only applying to some of the schools, but more than the outsiders, we can come up with examples in which introducing the common application favors the insiders and hurts the outsiders. Because in all these models, what's in the background in all the results, some people are not applying. When you go to the common application, the people who apply to all the schools, but you may actually deter some people who were applying before from applying at all, because the admission probabilities have gone down. And if I only care about one school, for example, I might apply to that school under the decentralized case, but give up in the common case, because I'm like, oh, that school's flooded with applications. I don't want to go there. So you can come up, we have some examples in which the common application ends up promoting insiders to apply for many of the schools to all of them, and can drive outsiders out of the market. So there's ambiguous results. So we're going to come to the empirical data with the view that I have some hypotheses coming up. We're going to come to the empirical data with a view that the common application might be actually counterintuitively bad, especially from the perspective of matches, but that we don't know whether it's truly going to be good or bad for the disadvantaged students. And I should come back, I'm not really sure we're trying to decide whether it's worth it to say this, but kind of an obvious point is if you don't necessarily know in advance that the common application is going to be good for the outsiders, a natural thing to do instead is to put in quotas. Say, well, we've got representation at 10% right now at each of the schools. Why don't we just make it 20? And we'll run a system, we'll run any system, run the decentralized system, but give more of a priority, coming back to some of the models many of you have probably worked with, give more of a priority to the outsiders, make it very explicit. Don't try to do this in sort of secondary fashion by changing the admissions rules and hoping it works out. So that seems like such an obvious point that I'm not sure it's worth writing it down, but I think it's appropriate to mention it here. And I'll be curious for views from others of you about whether it's worth it for us to include results like that when we formalize the working paper. Okay, so the empirical setting, and fortunately we have a good deal of time, and there may even be some time for additional discussion at the end. The Chicago Public Schools introduced a system for assigning students to kindergarten and high school. It had always had a mixed system. We are still trying to parse our way through this. It's going to make the results actually less clean than they would be ideally. Some spots in schools are assigned by neighborhood priorities, and others are assigned by a formal application system. Traditionally, the formal application system was this decentralized case. You filled out one sheet of paper for each school. Sometimes I think you had to even mail them to the schools. And anybody who studied New York, I believe that's the way it used to work in New York. And now, thanks to Parag and Al and Taifun and Attila and others, it's all much more sensible and a single application with rankings. What Chicago did was a version of that. They just simply cleaned up the system, and they said just check the boxes for the ones you want to apply to, so that that was their switch to the common application system in 2010. What actually held us back was that for most of the time that we analyzed this, we thought that this change was a different year. So the results didn't make any sense to us. I believe that I'm only going to present the results for kindergarten. I believe that it may be that they changed the system in a different year for kindergarten and for high schools. And so that doubly confused us. We verified there's only 4 high schools that use the system. When the high school switched to the common application system, all the predictions look exactly right, but there's only 4 of them. So I'm going to focus on the kindergartens, and we now know exactly the year in which the kindergartens changed. But this is but I'll be very clear in explaining why this isn't clean. And as clean as we'd like. The first reason this isn't as clean an empirical test as we would like is that it's not used for all of the spots, and the spots in each school vary by year. And it may even be that some people know, that school down the street, last year it had some spots, but this year it doesn't. And so we don't know. We observe how many students were applied. We observe how many students were admitted and how many enroll. Only a fraction, and in some schools a very small fraction of students end up being assigned to this formal application system, which is all we have the data for. I guess we have the data for the neighborhood system as well, because we see where people ended up attending, but that's very messy. We have 5 years of application enrollment data. Parag and Kara are right now working on trying to expand and clean up the data for additional years before and after. But I'm going to report for basically the first 4 years, 2009 and 10, which we know is in the decentralized case, and then 2010 through 11 through the first 3 years, which is actually 2012-13 of the common application system. We have data for I've analyzed data for the 4th year as well, and it doesn't look very different, but we are not as certain that that's clean. Those results are clean yet. And so I'm not going to show that 4th year. There's 4 hypotheses that are generated from the theoretical model. Remember, the theoretical model had to make strong assumptions about the symmetry of the schools. So one reason that if it turns out the results don't hold, it could simply be that, in fact, well, the results hold in the theoretic symmetric case, but they don't translate to the cases that are as asymmetric as Chicago. So that's certainly a possibility. We're going to test it as though the results do carry over. So the first hypothesis is that the applications per school are going to increase. The second one is that the admission rates decrease after 2009 to 10. All this is going to be pre-post. The matches were less efficient, and that diversity of enrollment increased. As a first point, I just want to show you that the number of participants, in fact, doesn't change very much. We don't have a hypothesis about the number of participants. I gave you an intuition for why the number of participants might decrease, because with the introduction of the common application, it used to be that I wanted to apply to one school, and the common application made its admission rate go down, so I say forget it. But it could also bring more people in, because I wasn't that interested in any one school. I wanted to apply to a bunch, and now it's free for me to do it beyond the first one.
So is there a way for people to get into a school without going?
Yes, and more than half of them do. They go to their neighborhood school.
Oh.
We believe that that's the rule. So we're still working on that. So the way I would think about this is that these are effectively the most popular kindergartens in Chicago. It's a big city school district. They've got some really good programs and some not so good. They've got huge variation. There are going to be some of them that are very particularly popular, and these are the ones where the excess spots, however many there are basically generated by this system. And so the way I would think about this empirical application is that these are people who are trying to improve on their default assignment.
And kindergarten is mandatory, right?
Kindergarten is mandatory, although any of these big cities are going to have this in the United States are going to have the phenomenon that rich families may be trying to go into the system for the best school, and if they don't get it, they'll go for a private system, non-public system. So that's a big feature in a lot of Parag's work on Boston and New York school assignments.
Well, there's a big jump from 2011 to 12.
Yeah, I don't know. So that's a good point. It looks like it's fairly stable, and it looks like there's a big drop down in 2012. 2013, I believe comes back up, although I'm not. It looks like there's something unusual about 2012. I agree with that. But the thing to see here is that at least for the first 2 years, it's fairly stable. About a little bit less than 2,500 plus or minus families and students are applying for kindergartens, and so it doesn't look like the introduction of the common application changed overall participation very much.
And do you know what the total population? Proportion to the population?
Not offhand.
So this is 3 years old or high school?
This is for kindergartens. There's just only 4. So this will help with this. Only 4 high schools participate in this lottery. So I'm not showing the results for those because that's too few. There's a huge variation in the number. There's actually more than 300 kindergartens that participate. I don't know how many there are overall. That's the fact I don't know. But that's obviously a knowable fact. There's about more than 300 that participate every year. And there's a huge range of them where some of them, these are the average number of applications after the introduction of the common application. So some of them are getting very few applications, but at the right tail, there's about 50 plus that are getting 101, 201, more than 500. These are the really popular ones.
So I thought that when you did the common application, automatically it would be sent to every.
Well, not with 375. So there's a rule. The 375 was the maximum participation. There's a rule that you can do at most 20. So it's not a pure common application version. And even then, it's a little bit rare to hit the maximum.
And so people actually need to.
You identify, yeah.
Wow.
I think that the view here is that it would just, with this, it's an interesting question. It's an interesting market design question, which is, would it be more efficient to assume that everybody applied to every school, run the algorithm, and then send, and what you would get is you'd get a letter that said, you've been admitted to the following 37 kindergartens, which might be, in some sense makes it easier on the application stage, but perhaps harder on the decision stage.
But for your theoretical results on common application, you assume that you apply to everything. So
absolutely. So
maybe the comparison.
So I want to. So that's yet. So there's.
Common application, because here you make a selection of 20
absolutely.
places, right?
So two big reasons that the theoretical results aren't going to apply. The one that I highlighted, which is just the variation. There's a lot of asymmetry here. And the second one that both of you are pointing out, which is that it could be important that it's a truncated list. The truncated list isn't going to apply to the high schools because there's just 4 of them. But even then, it turns out that it's a choice, and many people don't apply to all 4.
But there were like 300 different kindergartens here.
There's 300 different kindergartens, yeah.
And all the information you have in the web page, basically, where you check the boxes, is the name. So
yes.
You might even not know where some of the kindergartens are. You don't have a map or anything.
No, and we find a strange. In fact, less than so. I believe it's only about half of the students who get admitted to one of the places they apply even choose it. So half of the people participate in, half of these 2,500 students among the 2,500 students who apply, some number of them, a little bit less than half get any offer, but a little bit less than half of those who get an offer take one of the offers that they get. So that seems paradoxical in advance. It's suggestive that they don't really know that much about the schools that they're choosing. Yes?
Thing is not clear. So how do these two application procedures are connected? So you can either go to the local school or to apply through this system.
Or you can apply to this system and still not make the choice of any of the schools that you get. So you submit your applications, you fill out the sheet of paper, you check the boxes for up to 20 schools you want to apply to. You are told sometime later you have offers from the following schools, which may be 0, but often could be a few. And at that point, you say, okay, I have the choice of my default assignment or one of the 3 schools or the schools that have made me an offer. So in a world of certainty, you'd only apply to schools that dominated your default assignment, but that's clearly not what's happening here. Okay, so to test these 4 hypotheses, and mostly what I'm going to show you, the results actually are the results are very clear. So we don't need to do anything very tricky. But there's one more challenge, which is that reporting got better. So in fact, 175 kindergartens reported applications each year. But there's actually about 100 more that reported applications after the adoption of the common application than before. And we are still trying to figure out if that means they didn't participate before, and they just reporting wasn't so good because the whole system wasn't centralized, or they were induced to participate only after the common application was introduced. So so this is getting kind of messy. We're going to limit analysis to the schools that had applications each year. And with the caveat that at least we see that participation didn't change that among the student side, didn't increase that much, at least in the first 2 years after the introduction. So here's the average applications per year. We're looking for a structural break after 2009. You can see why we were confused when we didn't have the right year correct. We didn't have as anybody did, the interrupted time series. If you don't know when the interruption is, it's hard to interpret the data. And we do see a jump of about 20 to 25% in applications per school going from 2009 to future years. Even in 2012, where the participation was down for the number of students. The average number of applications received per school has increased. So that seems at least to be fairly consistent with the idea that when you introduce the common application, applications per school go up. It would be kind of shocking if it didn't happen. But that doesn't mean, but for a while, when we thought that the break was in 2010, that's what we thought. We thought, oh, it didn't really happen. But I think actually it does. And another nice point, I think, is that if you break out the kindergartens by size, by the quartiles in terms of average number of applications after the fact, there's no clean way to divide the kindergartens without making self-referential to the number of applications. So here we're doing it based on the number of applications they receive after the common application. There's about a 20%, this vertical axis is the increase in applications. So average number of applications divided by schools. Average number of applications per school after versus before. There's about a 20% increase in every quartile. So it's across the board increase in applications. That's at least reasonably satisfying. The results get more complicated when we look at the admissions rate. So if I actually say, let's just compare the admissions rates school by school by school. All these were comparisons school by school by school. Let's look at the admissions rates. The prediction was more applications, lower admissions rate. Well, that proves to be highly quartile dependent. So that same division of quartiles. If I look at the smaller schools, the ones that don't get very many applications, especially the very small ones who are admitting almost nobody before, and they have a huge jump in admissions rate afterwards. I can't explain this, except that these are very small schools, and in fact, it turns out that they almost, even though they're admitting a lot of people, almost none of the students they admit ever come. So it could be that they just started to realize that, I don't know, that they weren't doing very well, they weren't actually filling their spots the way they wanted to, but this is anomalous. At the other extreme, the larger schools, and these are basically receiving 0 to 10 applications, 11 to 25. This is quartile 3 is, maybe this is 11 to 40 or so. This is about 40 to a little under 100, and this is 100 or more. The schools that are receiving a lot of applications really did reduce their admissions rate. So if you think about this as, at least at that end, really popular schools being targeted by people who are looking for a dramatic improvement over the schools that they're getting from the default, then it looks like the model that the predictions do apply there. But already, as I said, this is not working across the board. So if you try to do a more sophisticated test, it all turns on how you treat the smaller schools. Yeah.
Schools in quartile 1 and 2, they are under capacity in September?
No, they're just receiving fewer applications. They're not particularly under capacity, as far as we know.
Just one thing. So this is these quantiles are about the size.
This number of applications? No. It might be correlated with size of school, but it's it's just the number of applications you're getting per year. I should look more to see if it's correlated with the size of the school. I don't know. So it would be helpful if when we chat about this afterwards at lunch and other times, it would be very helpful for you to tell me how I should try to refine these analyses and what I should look for in the data, because as I said, we find these patterns a little confusing. And I have only a couple minutes, so I will say, I'll skip the matching efficiency, and I'll say just the diversity, which is really important. This was the motivation for the whole system. There's basically no matter how you would look at it, there's essentially no change in the diversity, either of the applicant pool or the set of students enrolling at any of these popular schools. We mostly look at the popular schools that are receiving lots of applications. They got lots more applications. They didn't get proportionally more from minorities, students who were income disadvantaged according to the records, or anything else. They got about this, the applicant pool across in distribution looks about the same as it did before and after, but it's bigger afterwards. And the set of students who are enrolling look the same. So basically what the common application seems to have done is pumped up applications for every group by basically a similar proportion at those bigger schools.
So can you just make sure I understand? So when you say the pool of applicants look the same before and after?
So it was, if it was.
Is it the intensive or extensive margin, something like that? So do the people who used to participate are participating?
We can't know. So we can't.
Do you also increase
we can't know about intensive, because it's year by year. We're comparing a pre and a post. We can't know. But it essentially, African American, Hispanic, Asian applicants all are up by the same percentage as none of every applicant is up by 20%.
Yeah, but, but it's up in terms of number of applications.
Yes, number of applications.
But a number of applicants.
No, by school I mean. Oh, that's important. So I'm looking at if you look at any one popular school,
Yeah.
and the hope is that afterwards it's going to have more students who are minorities, more students who are low income. It has the same proportion, and the reason is that at each school, it had the same in its larger applicant pool. It has the same proportion of individual groups.
But are you really getting a larger applicant pool, or
Yes.
just more people applying of the same pool?
I think it's more applications per person.
Yes.
Of the same. So there's two different ways.
You've looked at applications and not applicants, right?
Yes. Yeah. It doesn't matter. It's not the diversity. Basically, no matter how you want to look at it, diversity didn't change. And then naturally enough, when you get through the whole thing, enrollment didn't change. So the one thing that I think is very clear from this is that if the point of introducing the common application was to change the nature composition of enrollment, that failed. Nothing changed.
If you have different sizes of these kindergartens, actually that changes, right? Because if you're keeping the same, if increasing by the same ratio in all of them, but they have different capacities, it seems like people are applying less in the smaller kindergartens.
It does seem, no, there's something going on. Yes, there's this unusual diversion of people from the smaller kindergartens to the larger ones. I think that the smaller kindergartens are a red herring in the American idiom, are a distraction, because they actually typically they enroll 1/10 of a student per year through this system. So a lot of people are applying, but maybe even if anybody's applying, nobody's going there. So we might as well ignore them. But you're right that there's complicating heterogeneities. I'm over time, so let me just conclude by saying that I look forward to discussing, soliciting advice from you on all of these points, theoretical and empirical. But I think this is an interesting idea, but a misplaced idea that this particular common application rule was going to do much for diversity. And if it's not doing anything for diversity, its theoretical properties look pretty bad. So it seems at this point like I would say I'm fairly negatively inclined about its application in Chicago and elsewhere. And, but I'm open to lots of additional views and comments from all of you. So thank you very much.